Okay, so let's see here. This is where we were last time. We were reminding ourselves of what a single variable integral is. Again, keep in mind one of the purposes of this is that you got to know what you're generalizing before you can generalize it, right? And so just to be extremely clear, an integral is a Riemann sum. We define integrals as Riemann sums. Now, why is that? Is it because mathematicians like to be, formal and rigorous? That's part of it. But very important to understand, and we talked through a bunch of this last time, you really need Riemann sums, for not for abstract mathematician purposes, but for practical. Let's get the job done. We're building something here kind of applications, because you cannot make any immediate argument between most of those applications, in most cases, and just claiming, oh yeah, that's equal to area. What? How does that work? That's not a reasonable argument, right? Any version of that is reasonable, in fact, is kind of flirting with the idea of a Riemann sum, but just without wanting to actually come out and say it, which is a little dishonest. So there is no argument here to be made. And so if you are interested in one of these applications and you want to get down to an answer, how are you going to do it? Well, you have to make the connection that you're that you're going to form a Riemann sum, and then handy at that point that's already what an integral is. No need to make some argument about how Riemann sums represent areas and areas are integrals or something like that. No, you don't need an area at all. Riemann sums are integrals. Compute with the fundamental theorem. Boom. Right? Okay, so Riemann sums really, really important, and in particular, then that is what we're going to be trying to generalize, right? When you want to generalize the idea of a single variable integral, we're therefore going to be trying to generalize the idea of a Riemann sum. Okay, all right. So here's I kind of waved my hands just a little bit at this business down here, and this is just where I try to make that transition. Here's our single variable Riemann sum right there, and what's going on, right? What is this construction? And again, hopefully y'all remember all of that from long ago, so I'm not going to repeat all of it. But the big idea is you take your domain, you chop it up into little pieces. That's the first thing. Okay, well, let's try to generalize that. How do I generalize the idea of slicing this up into little pieces? Well, I'm going to have to take my domain, which is now a two-dimensional region, in particular a rectangle, and I got to slice it up into little pieces. For example, something kind of like this maybe. But then I got to keep going, right? I've got to slice this way as well. Now I've sliced it up into a bunch of little pieces. And notice that in the process of slicing up our domain into pieces, I've also sliced up my sort of x-axis interval, my x-axis shadow, you might call it. And I've also sliced up my y-axis interval as well. And so you'll notice that, in fact, just like we have these old formulas for how to slice up the x-axis interval, right? Well, we get totally analogous formulas for how to slice up the y-axis interval. And so I'm going to encourage y'all to look through and think through, why are these dark blue formulas totally analogous to these purple formulas? And effectively, that documents exactly how we're slicing up the domain. Okay. Next step in the process. Let's see. First of all, let me get rid of all of this. This is a huge mess at this point. Next step in the process. On each little piece here, I write down this expression. I write down f times delta x. So let me say that differently. I write some function times the size of that little piece of the domain. Now, before I go on to generalizing that, just a quick word. Why would I do that, right? Why are we writing down some function times size? And the answer is because in every application, in some sense, if you interpret the following appropriately, we're always multiplying a density times a size to get a quantity. Right? So if you're interested in the mass, how much mass is associated or collected on this little piece of the interval? Well, then you multiply mass per unit length times length. If you're interested in the population of whatever on this interval, well, then you population per unit length times length. It's always stuff per unit size times size. That we then, of course, limit of a sum means we're going to add that up over all the pieces and, try to get the round off errors to go away, etc. Right? Is that a... No, okay. Okay, so, all right, so keep that in mind. And by the way, one of the big misconceptions, one of the big sort of stumbling blocks for students about single variable Riemann sums is they keep thinking to themselves, well, yeah, but what is f? And yeah, I get that, right? We want to know what things are. If we're going to write down formulas, we want to know what the stuff is that we're writing down. And subtle but critical point here, it's very important that we not specify what f is. Because as soon as you specify what it is, like a lot of people like to say, oh yeah, f is height. Okay, well now you pigeonhole yourself. Now it's only height, and now this can compute only area, and now you can't do any applications anymore, right? So the slick move, one of the critical bits of strategy here is that we don't specify exactly what f has to be. This could be any sort of quantity per unit size for any sort of quantity that we might be interested in and for which certain particulars work out, so that this construction can apply to, as broadly as possible, to compute any sort of accumulating quantity. All right, so with all that in mind, we're going to do the same thing over here. We got some little piece there, and in the same way that I'm going to add up over all the pieces in single variable, well, likewise, I'm going to add up over all those pieces here too. But what am I adding up? Well, on this piece, just like in single variable, you should interpret this part of our developing expression here as stuff per unit size times size. And check it out, delta x, delta y gives me width times height. That gives me area. That is the size of that little piece of the domain. It's just that now size is area, not length. I mean, it's two-dimensional, right? If you want to talk about how big something two-dimensional is, you talk about the area. Right? Everybody happy with that? Okay, so this is our new expression. This is what we got. This is our kind of two-dimensional natural extension of what works so powerfully in the single variable case, the single variable Riemann sum. This is now a sort of a multivariable Riemann sum, and that is our definition of a double integral. In this case, we're keeping it two-dimensional for the moment. So what we call a double integral, which we denote like this, is defined to be that expression that we were just looking at. Everybody okay with that? Everybody see what the strategy is? A couple things to say about notation. I hope this comes as no surprise. This represents area, so I think that's a pretty reasonable thing to call it dA. Differential amount of area represents a little piece of area. We're going to eventually take a limit, and it's going to get smaller and smaller, etc. But this represents a little piece of area. And the other thing I want to point out, you look at this part of the Riemann sum notation. This is where the summing is happening. But notice we have to add in two directions. Both I and j have to vary over all possible values, because I need to add up not just this way, right, but also that way. You got to add up in the full range in two different directions to get all of the pieces. And so that's why, because there are two summations happening, arguably, we use two of those integral symbols together. And I would encourage you actually to think of this as a single symbol. This is what I'm going to call the double integral symbol. Right? Very importantly, this is not a single variable integral of a single variable integral. This is a different critter. This is a summation where I'm adding up n squared different terms where I've multiplied some density times some area. And there is no single variable integral in what I've written down here. Does everybody see that distinction? Okay. All right, now here's some good news for you. The book has some stuff in it. I've noted on the content syllabus that you are not responsible for. So the book talks about irregular partitions and test points, and there are really, really good reasons for that stuff to be done. But it's not appropriate to this course. It really makes more sense in a higher, like a real analysis course, something like that. That becomes highly appropriate and again really essential if you're going to develop these ideas. It turns out there's a lot of sticky issues that come if you're casual and careless about always slicing up in an exactly methodical, regular way. Bad things happen. And likewise, if you just arbitrarily pick the right top corner of your body, that's arbitrary and bad things can happen, and that's not what we're here to talk about. So we are in this luxurious position of looking at continuous functions. And when you have continuous functions, it turns out none of this matters. The sticky issues that we're worried about that motivate us to do this other stuff never happens when your integrand is continuous. So we're not going to worry about that. Okay. All right. So let's see an example. Now this is arguably a silly example because we've already answered this question, right? So we've already entertained the idea of a graph and looking over a rectangle in the domain and asking about what is the amount of volume under that graph and above that rectangle. Right? We already know how to answer that question. We've gotten an answer. It's iterated integrals, right? But I just want to point out as an easy starter example, and I have a secret motivation that I'll reveal in just a second, that this is also something that we could do with a double integral. And in fact, it's arguably more natural done with a double integral because I can just ask one little piece at a time, okay, how much is this volume here? The total volume is clearly the sums of those individual little slices, little French fries of volume, right? And I think it's a pretty easy pitch that volume is the height, namely z, namely f of x, times the area of this little piece of my domain, and we already decided that areas of little pieces of the domain, that's delta x, delta y, and then lo and behold, I mean, it just worked out really nicely. This is exactly the definition of a double integral. So isn't that nice? Double integrals are an alternative way to write down an expression for how to compute the answer to a question that we already knew how to answer in a different way. Okay, so here's my secret motivation. And this is hard to see coming. Again, we had previously computed volume with iterated integrals, namely like that. We just now computed volume. I wanted to switch the color. We just now computed volume with double integral. And the very powerful, surprisingly important conclusion we get here is because these two things, double integrals and iterated integrals, both answer the exact same question. That means that because they're computing the same thing, they are equal to each other. Everybody see that? Not clear why we care. Right? But there it is. Okay, now let me tell you why we care. And this is super important, certainly for this class. This actually turns into a very convenient computational strategy. This is why we care about double integrals in the first place. All right, now let me just remind you what we've done so far. We started this whole thing by asking about volume under a graph. We constructed iterated integrals. You can crank that out with the fundamental theorem to get an answer. And then, well, we asked, hey, can I compute the mass distributed over an area with an iterated integral? And we had to recognize no. And it doesn't make any sense. The argument, if you try to just directly write down an iterated integral to represent mass, the pieces don't fit together. It just doesn't work. So can't do that. And I argue also that if you were to just try to directly claim that mass is volume, just, yeah, of course, no. Nonsense, right? That doesn't hold water. Again, the question is not whether the statement is true. The question is whether the statement follows, right? Does it make sense? Is that a reasonable argument? Not is it a valid conclusion, is it a reasonable argument? And no, that is not a reasonable argument. Okay, so we just seconds ago made this seemingly pointless connection that volume could be computed with a double integral. And then we reminded ourselves that volume is also computed with iterated integrals, and then we concluded, therefore, that double integrals are equal to iterated integrals. That was just, again, a couple of minutes ago. Okay, so that's what we've done so far. Everybody kind of see that this is kind of a diagrammatic summary of sort of where we're at, right? And so here's why this all works and it all fits together. Because we now have a 3-step process for turning questions into answers. Right? We needed all of these pieces to sort of get that to fit together. Right? And so just to be very explicit, I'm going to do an example in just a second here. You've got to show all 3 of these steps. Right? If you want to have what I'm going to call for Math219 purposes a full argument. Explaining how you turn an application question into an answer. There's just no getting around the fact that the double integral aspect of that is very important, because if you don't have the double integral argument in there, then it looks like you're doing this, and that doesn't hold water. That's not a reasonable argument. Right? So we really need to first take our application and express that application as a double integral. And then there's really kind of no controversial questions about the next step. We're going to rewrite that as an iterated integral. We already have a theorem saying double integrals are iterated integrals, and then we're going to compute, just like we've already done previously, compute iterated integrals with the fundamental theorem and get answers. Yep.
What's the difference between a double integral and iterated integral?
Yeah, they're just completely different. You can look back at the definitions. They're completely different formulas. Right? So if you look at the definition of a double integral, we're multiplying mass, quantity per unit area times area. That's never been done in a single variable integral. Right? Single variable integrals multiply some quantity per unit length times length. And an iterated integral is where you put one of those inside of another one of those. They're just completely different constructions. Does that make sense? Yeah. Now, what does throw a lot of students, and let me come back up here, a lot of students focus way too much on notation. A lot of students are like, wait a minute, isn't that kind of the same as that? Oh my gosh, no, not at all. That's notation. This is a symbol that I just made up, right? I mean, what if I had just made up a different symbol here? No one would be confused as to thinking these are the same thing, because it's just notation. So great question. Thank you for asking that. It is very easy to get oversold on the similarity of the notation, and that's kind of unfortunate. But again, once you accept that these are mathematically different from each other, I mean, let's face it, the value of this is equal to the value of this. That is convenient. It is kind of natural to make the notations look like each other because of that reason, but it does create these confusions at the start. Okay. Alrighty. Okay, let's do one. This is the question that we got bogged down on. Oh, yeah, sorry, go ahead, yes.
Yeah, I guess this is another notational question.
Yeah.
For the double integral,
Yep.
there's, instead of bounds, you have an R, so is that just like another way of...
That's, yeah, if you come back up here to the definition, R is that's how we recognize in the notation what the domain is. The rectangle over which we're adding stuff up. Yep. And just making it a subscript is just an easy way to have it put in there.
Does it have to be a rectangle?
For the moment, yes. But we're going to very soon we're going to entertain what happens when it's not. Yeah. Okay. So let's do one. And again, don't forget 3-step process. And again, for Math219 purposes, we've got to show the 3 steps because our argument needs to actually make sense. And yeah, so anyway. Okay. So probably saw this coming. We're going to compute the mass on a rectangular sheet where mass per unit area is given. And again, this is the one where we stumbled previously. This is the one where we tried to write it down as an iterated integral and we crashed and burned because it doesn't make any sense because we're multiplying mass per unit area times width. What is that? All right, it's not a thing. It just doesn't work. Okay, so what we can do now is let's get my colors straight, dark blue. The very first thing is I can argue that mass is an accumulating quantity. The whole is the sum of the parts. If I were to take that region and chop it up into little pieces and add up the individual masses, that gives me the total mass. That's how mass works. Now that's an important part of the argument. Just to be clear, just because you have a formula, just because you have a name and a notation for something, doesn't mean that it's an accumulating quantity. Perimeter is a nice little counterexample. The sums of the perimeters of all of those little pieces is way more than the perimeter of the whole. Right? So this is not to be taken for granted, right? You got to always think, whatever your application is, wait a minute, is the whole the sum of the parts? And very often, such as with mass, well, yeah, of course it is. All right, and then we know that on any individual piece, mass is mass per unit area times area. And then we recognize that this is the very definition of a double integral. And so as we should have, we have now made an argument. Let's try to get this all on the screen here. We have made the step 1, phase 1 of the argument here. We have turned our application question into a double integral. Okay, step 2. When you're talking about a rectangular domain like we are here, step 2 is always pretty straightforward. We've got it right here. Step 2 is just the recognition that if you have a double integral, you can rewrite it as an iterated integral. Bounds and everything, it's exactly what you would hope it would be. So step 2 is, oh gosh, what happened there? Oh my gosh, my pen's freaking out. I don't know what's going on there. What in the world? Okay, I think that was my pen's death throes there. What is going on here? It's not erasing. Maybe if I hit back arrow. Okay, maybe if I scroll and go back. Okay, that's weird. Okay, sorry. I wonder if this pen's actually okay. Nope. Sorry for the technical difficulties. Okay, so step 1, mass is a double integral. Step 2, double integral is an iterated integral. And then step 3 is just the fundamental theorem of calculus. Y'all know how to do the fundamental theorem of calculus. All right, we did a couple of examples of those. Plug and chug. Don't forget for the inside integral, the outside variable is a constant. We've got to keep that in mind. And plug and chug. And we have turned our question on which we crashed and burned severely last time into a 3-step process that gets us an answer. All righty. Now, there's a quick thing I want to say about notation here, and this is just this is it's just notation. People, again, very often get a little too sort of focused on the notation. The observation gets made that, look, this whole limit summation thing, that's eventually, pretty much that's going to turn into this symbol. And so a lot of people like to kind of do that in advance and just go ahead and use that notation all the way through to just it's sloppy. Okay, we have never defined this thing by itself. Right? This is just math slang. Right? Math shorthand for the Riemann sum that I've got written up there. So that's actually pretty common. And then likewise, eventually differentials are going to turn into, I circled the wrong thing. Eventually deltas are going to turn into differentials. And so a lot of people like to go ahead and do that early as well. Right? So a very common and reasonable notation for this development that we just talked through, our step one, would be to say m double integral dm, that's just whole as the sum of the parts, and then pick your favorite notation for how to rewrite that as a double integral. Because after all, mass, little piece of mass, is mass density times size. Okay, so very common, very reasonable. I'm a practitioner myself. Feel free to do this kind of thing. You're definitely going to see this kind of thing going forward. Just make sure that you realize, don't believe your own sloppiness, right? There is no m-axis, right? That's not what that means. And furthermore, make sure you realize that when you write stuff like that down, what you're really doing is you're just kind of shorthanding the Riemann sum development that we've got there. Okay. All right. So related example. This is just, I'm not going to do most of this example, but I want to point out that sort of notational business. So here we have a hard problem. We're building a wall. I like to think of this as there's kind of a stone wall on the front face of my house, and it occurred to me at one point when I saw those guys building that wall that, man, those bricks are heavy. They're doing a lot of work. Just the lifting of the bricks that were on the ground, lifting that up to the level where they put it in the wall. My gosh, how much work are they actually doing just with the lifting? Right? So I thought that was an interesting question. So the thing that's going to make this complicated is that the weight of the bricks corresponding to a little piece of area on the wall is not constant. This wall had the thickness is different at different parts of the wall. Some places it's thicker, some places it's thinner. And so how many pounds per square inch is not a constant. Okay. All right. And so with that in mind, here's the argument we make. Work is an accumulating quantity. Now, again, let's just take an appropriate moment to think about, is that true? The amount of work that it takes to lift one brick at a time, if you add up all those amounts of work, yeah, it gives you the total amount of work of having to lift all the bricks. So, again, we've got to doff the cap to recognize that, yes, indeed, we are computing an accumulating quantity. Okay, next. What's going on here? And I claim all this says is work is equal to force times distance. You want to know how much work it takes to lift that one brick? All right. Well, you're lifting something that has a certain amount of weight. I'm going to call that dF. There's a differential amount of force that is the weight of that one brick. Right? And that is being lifted a distance, which you can see from the picture is just the y coordinate of where that brick goes. Right? So again, all the details about the geometry and the physics of the picture, but ultimately that's just work equals force times distance. Okay. All right. Is everybody happy with that? Okay. All right. right? And then let's see here. This right here is another. You just kind of have to think it through. Again, we're just talking about the one brick here, and this just says weight dF. By the way, just a little physics side note: weight is force, not mass. And so, anyway, so the weight of that little brick is weight per unit area times area. So, which you might call this a force density, right? Or it's a weight density. But weight, stuff, accumulating quantity of stuff is stuff per unit size times size. Is everything okay back there? Okay. All right. Good. Okay. All right. So. Everything else is kind of plugging in because if you look at what we've got here, I mean, y is already in terms of x and y. Density right there is in terms of x and y. dA is, take your pick, dy dx or dx dy, right? And so you can just turn all of this into a iterated integral, and you can then compute plug and chug. Details for y'all, again, we've talked about how to compute iterated integrals. And it's a healthy exercise. Go ahead and make sure you plug all that in and make sure that all works. Make sure that you can follow all of that. How we doing? Everybody's happy? Okay. So again, the purpose of this example was to show you how, in practice, you might see this kind of, again, arguably a little sloppy the way I wrote this stuff down, but it's very calm. It's very convenient, much more convenient than writing all this stuff up here in, full Riemann sum notation. It's just more convenient. Okay. All righty. Okay, somebody asked earlier, I've already forgotten who it was, is the domain always a rectangle? And I'm going to phrase that differently. What do we do if the domain is not a rectangle? And just to be clear on what I mean by the question here, what if you have a part of a graph, so some surface, right, graph, and your domain over which you want to compute the volume under that graph. What if that domain is not a rectangle? As you see in this picture, look at this. This is definitely not a rectangle. This is some wacky, weird sort of shape. How does all this work? Can I do this? Is this or am I out of luck at this point? Am I dead in the water? It turns out everything's fine. Now, there's a lot of formalities that go into this that I'm going to sweep under the rug, right? How do we define, how do we formally write down the official, rigorous definition of what we mean by a double integral on a non-rectangular domain? Oh, yeah, that's a lot that needs to get said there, and that's a Math 431 thing. That's not a Math 219 thing. It's just formalities. It's nothing to worry about. It's exactly what you think it is. We're going to take that shape and chop it up into little pieces, and then we're going to add up over each piece, right? It's exactly what you think. Nothing to worry about there. Can we compute this volume with an iterated integral? Yeah, totally. It works just fine, and I'm going to walk you through how this computation works. The total wrong color. The total volume, right, is going to be the sum of the volumes of these little, slices of bread there. Right? So I just need to ask now, okay, what's the volume of that slice? Well, it's area times thickness, just like it was before. How am I going to compute the area, you say? Right, so this in particular, that cross-sectional area, how do I compute that? Well, that's area under a curve. I'm going to compute it with a single variable integral. It's exactly almost, there's a little sticky wicket I swept under the rug. It's almost exactly the same as what we did before. So hopefully no surprise, we get an iterated integral again, right? And here's the only thing that's practically speaking different. That only thing that's different. And I'm going to zoom in if I can. Come on, here we go. Only thing that's different. Let's think about when we do this inside integral. That inside integral, remember, its job is to help me compute that area. Actually, well, anyway, yeah, it's helping me compute that area up there. Right? The integral is going to start at that point, which has an x coordinate, which is our lower bound. That's all just like previously. The only thing that's different is that where that point is and what that x coordinate is depends on y. And you can just see that happen. For different values of y, I would have a different starting point, which would give me a different coordinate. And that's just because it's not a rectangular domain, and I can't just go around assuming that this edge here is a straight line. It's just not a straight line because this isn't a rectangle. That's the only thing that's different. Everything else is good. Okay, let's see here. How do I get back to here we go. Okay, now here's a bit of good news. If you think about what we just talked through there, if I were to ask the natural next question, which is how am I going to figure out what that lower bound is, I argue from the picture, all that matters is where is this point that represents kind of the sort of the first x coordinate of the sort of the footprint of the slice that we're looking at. Right? So in particular, notice that all this three-dimensional stuff up here, irrelevant to that question. Right? How high is the slice has nothing to do with where my integral starts. That's going to compute the area of that slice. Everything that I need to determine these bounds is in the domain. It's only about the shape of the domain. The height, aka the integrand, doesn't come up. So this picture that I've got here, I think it's useful to sort of motivate the idea that we're still, when we're looking at something we're computing with a double integral, we're still, yes, going to be effectively computing with an iterated integral, yeah. But this is the picture we should be looking at to find the bounds. Just draw the domain. You don't need to draw the whole thing. You don't need to draw the graph. And let's see here. So the big idea, if you want to know this lower bound, just recognize that this being the range of values of x as we do the x integral in that direction, well, this lower bound is going to be determined by that point, which is on this curve. And if I know the equation of that curve, I can just solve for what I want. And keep in mind, in this case, what I want is a value of x. And so solve for x, and that will give you that lower bound. And so I've got that summarized. Let's see. Oh, whoopsie, I hit the wrong button. I totally hit the wrong button there. Sorry. There we go. Got that summarized right here. If you're interested in the bound, identify the corresponding point. That point's going to be on a certain curve for which there will be an equation. And whatever variable it is that you're trying to solve for, in this case, we're looking for an x coordinate because that's my x lower bound. Just solve the equation for that variable. Does it make sense to everybody? Everybody buy the strategy? Yes?
Instead of doing it on the x-y plane, could you project and do it on the x-y plane?
Not really, because two reasons. First of all, in this case, just for sort of visual convenience, I'm representing this as a volume, right? But in general, that's not what we're actually interested in. In general, we're interested in, I don't know, work or mass or some other thing, and then I don't even know what you mean, right? But secondly, because of the nature of the geometric question, I'm looking for the volume under. I know that nothing weird happens when I project straight down and look at that domain. But look, if I were to project into the xz plane, there's kind of a gap in here that how would I recognize that? I don't even know what to do with that. Does that make sense?
Yeah.
Yeah. Well, it's a good instinct to be thinking of alternatives, but yeah, in this case, the domain is intrinsic to the question, and the fact that we're looking at a volume that has projections in 3 coordinate planes is just, it's kind of an illusion. Yeah. Okay. Okay, let's see an example. By the way, the best way to get a handle on how to do this kind of stuff is to do a bunch of them. What you're going to notice as I go through these is I'm going to follow this process painstakingly with the first example, and then, I'm going to go through it increasingly quickly after we get a couple under our belt, right? But underneath every example I'm going to do is this process, and y'all, as you go through and do examples of this, should always think explicitly in these terms right here. You want to think the bound that you're interested in corresponds to what point, which is on what curve, which has what equation, and then make sure you solve for exactly the variable that you need. Okay, let's do this example here. So we're going to compute an integral here, and by the way, what application motivated that I would want to compute this integral? That's not really relevant to what we're doing here. Maybe I'm computing the mass over this triangle. Maybe I'm computing the volume. Whatever. Doesn't really matter. The point is I'm just going to start with the double integral, and I just want to talk about how to turn this into an iterated integral. Okay. Right. So, the first part is pretty easy. As we go in the x direction, my slices look like this, and you can see x is going to start at 0 and end at 1. That's basically staring at us right in the picture. So I think that's a pretty straightforward pitch. By the way, let's see if my stylus is working again. Nope, not yet. Okay. Okay, let's talk about the upper bound then for this domain. How am I going to find that upper bound? Right, that's going to be the upper bound for our inside integral. Well, that corresponds to this point. Thank you, picture. Can't do that without the picture, right? I need the picture to see how, which point is it that is the upper bound for my integral in the y direction for a given value of x, right? You gotta have the picture. And by the way, not only for your own sort of problem solving purposes, so you don't have to do it in your head, right? Very helpful to have a picture. But also keep in mind, you're communicating, right? Your goal is not to get the answer. Points come from explaining a thought process, right? So having the picture gives the grader something to look at and realize, oh yeah, this student totally got it, because look, you can see that point right there. It's clearly indicated, and now the grader believes you when you say you know what's going on. Right? So the picture is really, really important. Make sure you draw a reasonable picture. Okay, again, want to know the upper bound? Well, it comes from that point, which, by the way, is on that curve. Now I need to know the equation of that curve, and luckily, there are some given particulars. These are the 2 points, sort of there and there. So you do a little bit of high school algebra, blah, blah. Y'all can do that and confirm that the equation is that right there. So again, for that bound, that's the point, that's the curve, that's the equation, right? Identified the bound, the associated point, what curve, I've written down the equation. Next step, solve. And again, be very careful that you solve for the right thing. A lot of people play way too fast and loose with this. Let me clean up my picture, by the way. It's gotten a little out of hand. So a lot of people will look at this equation and just kind of write down either the left side of it or the right side of it or something like that, figuring, well, they're equal, doesn't matter. And that's wrong, right? We need to solve for the variable that we're interested in as a function of whatever else. And so just to be clear, right, we were looking for y2. y2 is a y bound for our y integral. And so in this equation, I need to solve for y. I need to be able to write y as a function of whatever else. In this case, the only else is x. And by the way, also in this case, the solving was super easy, right? I just made a really, really easy first example just to avoid, didn't want the distraction of tedious algebra. Sometimes you actually got to do a bunch of work here. But anyway, solve for y, nice simple formula for what that is, and that is our upper bound for our y integral. Does everybody see the process here? I'm not asking if you believe the answer. Does everybody see the process? Okay, let's do the same for the lower bound. We'll do the lower bound a little bit more quickly. Let's see here for that lower bound. Well, that's, again, keep in mind, this is our sort of x slice right there. That lower bound is the y coordinate of that point, which is on that curve, which has that equation. Again, you got to look at the picture to see what is the appropriate point, what is the curve that it's on, and what is that curve defined by, and how do I do algebra to get that equation. But anyway, that's the punchline. This is the equation that's ultimately going to determine what we need. And again, don't lose track of the fact that we're looking for y. We're trying to find the y coordinate of the starting point for this y integral in the y direction, right? So in this equation, we solve for y. And again, nice and easy, lucky break. And so our lower bound for the y integral is 0. Same process, different details. Cool? Let's do it again. Slicing the other way. Because we can. Right? So, okay, well, let's see here. It says here we're going to do our y slicing first. Okay, well, look, y slices look kind of like this. And they clearly start at 0, and they clearly end at 1. That's the pretty, again, staring right at us in the particulars of the picture and the givens. It's just 0 to 1, so that's pretty straightforward. Okay, well, what about, let's see here now, for a given value of y, there's what one of my y slices look like. This is going to be how I'm going to do my x integral. My lower bound for my x integral is going to come from that point, which is on that curve, which has that equation. Several step process there. Again, you've got to follow that process. Wait a second. What am I doing here? Oh, yeah, that's right. I am trying to find the x coordinate because I'm looking for an x bound. So I will solve for x in this equation. I need to be able to, in this equation, view x as a function of y. So the answer here is y for the lower bound for the x integral. And again, this is something a lot of people, some of you all have had high school multivariable calculus classes, and they're a little bit fast and loose with how they, all exceptions granted. But a lot of people will write down x for the lower bound. Because after all, y equals x, and they figure x is probably what ought to go here then, and that's just wrong. X is wrong. Everybody see what's going on? Okay. Super quick, just to wrap this one up. The upper bound comes from that point, which is on that curve, which has that equation. Again, I'm looking for the x coordinate because this is the upper bound for the x integral, so I solve for x. And the answer is 1. Same process, different details. There you go. Everybody good? Okay, we're out of time. See y'all later. Have a good rest of your Wednesday. And yeah, see you Friday. Don't forget about attendance, of course.